Hello and welcome to this module 13 of manufacturing systems technology. If you may recall, last module we were discussing about the Bezier fit particularly, and we talked about how a characteristic polynomial can be generated, which is also known as the Bernstein polynomial. And in that aspect, what we also discussed was that how instead of the earlier complex requirement of the slopes at the ends and the points at the ends in the Bezier fit, what is needed are only 4 different points across which you can maintain a curve fit only based on the point values and not the slope values. We also elaborated about how different curve sections can be connected to each other using a C1 continuity, where the radius of curvature, the center of curvature may be different, but there should be one tangent at the point of intersection of both the different curve segments. So, we are going to discuss a practical problem today of the Bezier curve fit. Let us look at this particular problem where we want to develop the equation of a Bezier curve. We want to develop the equation of a Bezier curve given the values of the t, the different values of the t as illustrated here on the curve, and the different values that we are investigating to formulate the points are t equal to 0, t equal to 1/4, half, 3/4 and 1, and we want to plot the curve for the following data points. Okay, so you have point v0, point v1, v2 and v3, and as it appears that all the z's are 0, so therefore it is actually a 2-dimensional case, it is a 2-dimensional curve that we are plotting. So, the first point is 0, 2 coordinate axes x and y, v1 is 0, 0 coordinate axis x and y, v1 is 0, 2, v2 is 4, 2, v3 is 4, 0, so on and so forth. So, we want to develop a equation using the Bezier curve fit. So, from the equation on Bezier curve, because the number of control points in this case are 4, that is n plus 1 equal to 4 or n equal to 3. You have already learned about this in the last class where it actually described and talked about the Bezier fit. So, given this, the Bezier curve function can be described as follows. Vt equals sigma I varying between 0 and 3 factorial n by factorial I factorial 3 minus I, that is 3c1, n being the maximum notation which is equal to 3 in this particular case corresponding to the 4th point, t to the power of I 1 minus t to the power of 3 minus I vi, that is how it is defined. And if you expand this, you can have the value of Vt as v0 1 minus t cube plus 3 v1 t times of 1 minus t square plus 3 v2 times of t square times of 1 minus t plus v3 times of t cube, given t varies between 0 and 1. Substituting the values now, and they are corresponding to the different values of t, 0, 1/4, half, 3/4 and 1. We simply have v0 obviously should be equal to the subscript v0. We are just solving this equation for the various values of t. v1 4th corresponding to t equal to 1 by 4 can be obtained as 27 by 64 V0 plus 27 by 64 V1 plus 9 by 64 V2 plus 1 by 64 V3. Similarly, corresponding to t equal to half, the equation gets modified to 1/8 V0 plus 27, 3 by 8 V1 plus 3/8 V2 plus 1/8 V3. So all we are trying to do is to put the value of t in this particular equation here corresponding to Vt to find out the various equations. Similarly, V3 fourth corresponding to a value of V equal to, at the point t equal to 3 by 4 can be represented as 1/64th V0 plus 9/64th V1 plus 27/64th V2 plus 27/64th V3, and that is actually nothing but the coordinates of the points that have been substituted and found before. Okay, so that has been found by substituting the values corresponding to V0, V1, V2 and V3, and these are the values which have been obtained earlier from the question. Remember, we had talked about these 4 control points which were the basis for creating this Bezier fit. I am just going to write this here. V0 was given as 0, 0, 0, right. So there is an x, y and z coordinate here which reads 0, 0, 0. Obviously, if I substitute the value of V0 corresponding to all the x coordinates, you obtain the x coordinates at these points corresponding to t equal to 0, 1/4, 1/2, 3/4, and then obviously there has to be a V1 which would correspond to only V3, okay, the end value. V1 was at that particular obtained question obtained as or given as 0, 2, 0. V2 was given as 4, 2, 0. V3 has been given as 4, 0, 0. So one thing very interesting about the Bezier fit here, the assumption basically was that the first and last points are on the curve itself. It's true here because obviously the x, y, z coordinates if put into these equations to solve for the various V0s to V1s become 0, 0, 0. So this is matching, as you see, with the first point V0. Okay, so V0 and corresponding to V corresponding to t equal to 0 and the point V0 are the same, so that's the last point. Similarly, V corresponding to t equal to 1 and the V3, the last point, are same, so it can be as well replicated as 4, 0, 0, the values of the coordinates. And so now we substitute the x coordinate of V0, x coordinate of V1, x coordinate of V2 and x coordinate of V3 and calculate this thing, and we obtain the value as 5/8. Okay. Similarly, if I plug in the value of the y coordinate of V0, y coordinate of V1, y coordinate of V2 and y coordinate of V3, we get the value 9/8. Okay. And if you plug in the values of the z value of V0, V1, V2, V3, all of them are 0. We know that we are talking mostly about a plane curve in this case. All the values of the z coordinates, as you can see here, are 0, and only the x's and y's are varying, so this becomes 0. Similarly, corresponding to V half, the coordinates become twice 3 by 2, 0. Similarly, for V3 by 4, the coordinates become 27 by 8, 9/8 and 0. So that's how you have mapped different values of t through which you can plot now, and if you really plot all this together, you get a curve like this, right, which corresponds to probably some value of t here equal to 0, t at the value t equal to half, and then t equal to 1 again, which is at this particular point, and obviously the t 1/4 and the t 3/4 are 2 points on this, and between these 2 points V0 and V3 there are several other points, like probably in this particular case V1, V2, V3 and the V4 point. Okay. So, these different points corresponding to the 4 different points which are also governing this particular curve, and the displacement of these points which may or may not be on the curve, okay, will actually control the topology of this curve very much. And that is how, without really taking care of any slopes across any portion of the curve, in this particular case by only the variation of the control points, you are able to vary the topology. So, that is how you can do the Bezier fit, for example, in a CAD situation or in a CAD problem, which can map a lot of variety of topologies between such control points in question. So, there are many other kind of fits which are possible, and I think I had mentioned about the B-spline, rational B-spline, non-uniform rational B-spline curves. So, as far as the B-spline is considered, a generalization of the Bezier curve is done in a manner to obtain a B-spline where there is some degree of local control which is there. Okay. So, for from the only difference between the actual Bezier curve and the B-spline is that local control becomes an interesting feature of the B-spline curves, and it can imply that any change in the local control affects only a part or a region of the curve. So, for example, supposing in this particular case there was a point V dash and it goes to another point V double dash. So, there is some kind of a change in the bending radius or the center of curvature of this particular curve because of the control or because of the changeover of this control point from V dash to V double dash. Okay. So, this feature is not available in a Bezier, because if you have only one control point changing, it may change the overall curve geometry, okay, or overall curve topology, and you cannot have a sectional change in that corresponding region governed by that particular point. The Bezier, in fact, the B-spline function is actually plotted in this manner. So, in fact, I mean this is not being covered now because here the mandate is to slowly move towards a little bit higher level manufacturing from the CAD process, and so the idea was to give you an insight on to how geometric transformations etc. are used to really now map everything in terms of coordinates. And interestingly, these are the coordinate systems which would formulate the output data for the CAD, and they would be maneuvered over the computer aided manufacturing systems to actually start producing the parts based on the coordinate data coming out of the CAD. So, that is what we are actually interested in right now. And before just proceeding ahead, one small important section needs to be done, because so far we have talked about only 2D curves and obviously some illustration of 3D curve, but a surface is much more complex than only a curve, because the surface is essentially an array of curves. Okay. And how to handle that array of curve becomes very important in terms of the level of computations. In a 2D curve, for example, the level of computation has been what you have already seen in the previous few lectures, but when you talk about a 3D curve and not only that, an array of such 3D curves which defines a surface, the expansivity of the computations becomes enormous, and you have to handle a very large volume of data. So, what I am going to do is to give one case study where we will talk about the Hermit cubic fit polynomial to map a surface without really going into all the local derivations involved. You have already done the 2D curve before, so by virtue of that you will probably be able to extrapolate that knowledge and be able to derive, but I will just mention the basic needs just to give you an idea of the expanse of computation which would happen if you go from a 2D curve to a surface case. Okay. So, let us talk about surface modeling a little bit. So, as obviously you know that in wireframe modeling we take the advantage of the simplicity of certain surfaces, particularly regular geometries, and a plane is represented by its boundaries. For example, this is a very regular geometry. We do not say anything in the wireframe model about the middle of the plane, which is fine because we know that the middle of the plane is still a sort of a plane. Okay. But obviously for complex shapes or irregular geometric shapes, when we talk about maybe a very complicated surface, it is not easy to represent that, and therefore surface modeling is preferred in that particular aspect. So, let us look at surface modeling from a little more detailed viewpoint. So, typically there are many ways of doing surface modeling. One of them would be just by representing a certain set of lines. Let us say in this particular case there are two curves which is represented by curve 1, in this particular case the curve 1 is somewhere like this, okay, and the curve 2 is something like this. Okay. So, this is a general curve and the set of curves, and what you do is to simply extrapolate the curve by making sections like just like a sort of a slat conveyor, and make different sections which represents the surface of the various sections of the curve, and that is how the whole surface can be mapped in this particular manner. So, this is a very crude way of representing the surface. Okay. Then there is another representation of the surface where we have a sweep line. For example, in this case there is a line here as one of the elements, and you are just rotating or sweeping it at an angle around an axis. Okay. So, there is another kind of surface generated, probably because of the revolution of this particular line along the axis. So, in this particular case the definition of the surface here is called a ruled or a lofted surface. In this case we call it surface of revolution based creation of a surface. Okay. So, surface of revolution. There are other ways, like you can have a tabulated cylinder where there is something called a directrix and a generatrix. The generatrix is basically the element which is needed to be generated, and the directrix is the direction in which this element would move. So, if it moves in a regular manner on a circle, we get a surface. So, this is another way of doing classifying any any particular surface with respect to a generatrix or a regular feature or a line, and a directrix which goes around. And then finally, there is something which is very complex, which is called a surface fit, which is represented here. So, if you look at the various surface entities based on whether they are regular or irregular, you can have these all different kind of representations, from a plane surface to a ruled surface to a surface of revolution to tabulated cylinder to a B-spline surface, to represent such geometries. Okay. Most complex is obviously this patch here, which we call a Bezier patch or a B-spline patch or a Hermit cubic spline patch, and I am going to actually now look into how to generate that patch in the next module. So, with this I would like to end the module here, and in module 14 we will discuss more about the patch formulation and how you can map that as a surface entity. Thank you.